Hey everyone, have you ever wondered if there's like a secret performance thief just hiding in your code? Something that happens behind the scenes, even in the simplest lines that can slow everything down? Well, today we are going on a hunt to find it. All right, so let's dive right into our central mystery. Take a look at this line of code. Object obj equals 10. I mean, it seems totally harmless, doesn't it? You're just storing the number 10. But what if I told you there's a hidden cost baked right into that simple line? A secret operation that can really drag down performance. Our mission today, let's uncover it.
Okay, so to find this performance thief, we have to understand the crime scene. And that scene is the computer's memory. It turns out our data can live in two very different worlds inside that memory.
Yeah, so inside your computer's memory, we've got these two fundamentally different places data can live. You can almost think of them like two separate neighborhoods. One is called the stack, and the other is the heap. And trust me, where your data ends up, it makes all the difference. So, to really get this, let's use a simple analogy. Think of the stack as your tidy, organized work desk, and the heap as a giant, massive storage warehouse. It's a pretty fundamental rule. Simple stuff, value types like numbers and booleans, they go on the desk, on the stack. But the more complex stuff, the reference types like objects, they get sent to the warehouse, the heap. Let's stick with that desk analogy for a second. The stack, it is built for pure speed. Imagine everything is right there, right at your fingertips, super easy to grab, use, and then just clear away when you're done. It's just incredibly efficient for those simple everyday values. And then you've got the warehouse, the heap. Now, storing a big complex object here, that's a whole other story. It's a much bigger deal. The system has to go find empty space, formally allocate it, and even create a little tracking number for it, what we call an address. It's really powerful for long-term storage for sure, but it is just inherently slower to get things in and out of. Okay, so we've got our two worlds, right? The fast desk and the big warehouse. Now, let's get back to our mystery. The very first clue we need to look at is a process called boxing, and that is the journey from the desk to the warehouse. So what exactly is boxing? Well, it's pretty much what it sounds like. It's the process of taking a simple little value type, like our integer from the fast stack, our desk, and wrapping it up inside a box so it can be stored as a reference type on the heap in the warehouse. It's the formal process of moving from one world to the other. And listen, this isn't just a simple move. It's a whole operation with multiple steps. First, your computer has to go find and allocate memory over on the heap for a brand new box. Then it has to literally copy the value from the stack and put it inside that new box. I mean, that is a lot of hidden work happening behind the scenes. And there it is. Let's bring it all back to our original mystery code. That one simple line, object obj equals 10. That is the trigger. You are telling the system, hey, take this simple value, 10, which belongs on the stack, and store it in an object variable, which has to live on the heap. And just like that, you've ordered a full-on boxing operation. But wait, the story doesn't actually end there, because, a lot of the time, once you've sent that data over to the warehouse, you're going to need it back at your desk to actually do some work with it. And guess what? That return trip has a name too. Yup, it's called unboxing, and it is the exact reverse process. You're taking that object from the heap, from the warehouse, opening up the box, and bringing that value back to the fast stack, your desk, where you can finally work with it again. And just like its counterpart, unboxing is also a multi-step process. The system has to go find the object on the heap, read the value that's tucked away inside it, and then copy that value back to a new spot on the stock. It's another trip and another costly copy operation. So here's what that looks like in the code. Whenever you see a cast like this, int object, you are literally witnessing unboxing in action. You're explicitly telling the computer, hey, go to that object over there on the heap, pull out the integer value inside, and give me a fresh copy of it back here on the stack. And with that, the round trip is complete. Okay, so we followed our little piece of data on its entire journey, from the desk to the warehouse and all the way back again. Now it's time to connect all the dots and deliver the final verdict. Why? Why is this our performance thief? And here it is, the absolute heart of the matter. Boxing and unboxing are costly for two main reasons. They involve memory allocation and they involve data copying. And let me tell you, neither of those operations are free. Let's just break that down a little. Every single time you box a value, you're forcing the system to go through the complex process of allocating new memory on the heap. And every time you box or unbox, you're doing a data copy. Now, look, a single one of these might not be a big deal. You probably wouldn't even notice it. But what happens when this is inside a loop that runs hundreds or thousands or even millions of times? Suddenly that performance hit becomes very, very real.
So what's the big takeaway here? Look, the goal isn't to never box a value again. Sometimes it's just unavoidable, it's necessary. The real goal is to be aware that it's happening and to consciously avoid it wherever you can, especially in those parts of your code that really need to be as fast as possible.
So, I'll just leave you with this one thought. Now that you know what to look for, now that you know the culprit, the real question is, where is this hidden performance thief hiding in your code? Because just being aware of this little journey between the stack and the heap, that's the first huge step to writing much faster, more efficient applications.